Welcome back to another fabulous Francois physics fantasticness. And what we are going to discuss today is how to solve a 3/4 problem, a 3/4 projectile motion problem, using a two-variable chart. So here's a example problem with our handy-dandy equations being listed out for us, as well as the two-prong chart, two-variable chart that I was referring to just before. Now, what you may wish to take the time to do is pause the video here, see if you can work out what the correct answer would be, and then follow along in my problem here so that you can see and make sure that you know everything that's going on and that you have done the correct work. So if you want to do that, take the time to pause this video now, and then I will lead you through it. Okay, so for those of you that paused, I hope you got the correct answer, and for those of you that haven't, please follow along. So, what we need to do is we need to break down this problem. Now, we have Green Arrow, the bow-wielding superhero, fires an arrow from a 20-meter high building with a velocity of 30 meters per second at a 35-degree angle above the horizontal. It strikes a robber in a second-level store of a mall, 5 meters above the ground. Horizontally, how far away from the store was Green Arrow? Okay, now we need to break this down as far as what's going on, what values do we know. So, before we can do anything with our fun, fabulous equations. So, let's see. Green Arrow fires an arrow from a 20-meter high building. That doesn't tell us anything quite yet because it hasn't said where yet, where it has landed. We see that later on, but we cannot take that and throw that into our chart immediately because it's not about the height that we put into there, it's about displacement, correct? So then let's go forward with it. So a velocity of 30 meters per second at 35 degrees. So that means my initial velocity total is equal to 30 meters per second at an angle of 35 degrees above the horizontal. So that's a positive 35 degrees. If it was below the horizontal, we would have had to make this negative. Okay, now in order to do anything with this, we will need to take this number and split it up. Now we split things up using our handy-dandy trigonometric functions because realistically what we're looking at here is this triangle right here that I'm drawing. We have our actual velocity vector of 30 meters per second. We know this angle right here is that 35 degrees that we were talking about before. And we're looking for our initial velocity in the y direction and our initial velocity in the x direction. Now, let's see if we can figure out how to do this. Now, if I want to find my y direction, I have the hypotenuse of this triangle, and I have the angle of this triangle. So if I want to be able to relate the opposite side, the hypotenuse and the angle, what I'm using from SOHCAHTOA, if you remember what it is, we're using sine, because sine of an angle is equal to the opposite side over the hypotenuse within a right triangle. Now I know the hypotenuse, I want to find the opposite side. So what I would use is I would have to rearrange this because I'm going to move the hypotenuse up over to the other side, seeing as how it's dividing from my opposite side. I want to make it so that it's multiplying, so that way I can cancel it out by multiplying it to both sides. And so we end up with 30 times the sine of 35 is our initial velocity in the y direction. And what we will need to do is figure this out by plugging it into our handy-dandy calculator, and when we do that, we get a value approximately 17.21. So that's our initial velocity in the y is approximately 17.21 meters per second, and that's upwards. Okay. Now if we want the x value, instead of using sine, we're going to end up using cosine. So our end result for this one is our initial velocity in the x, by the same logic as what we used with the y, is going to be the hypotenuse times the cosine of our angle. So that means that we are using our initial velocity in the x is 30 times the cosine of our angle 35, which happens to be, according to our handy dandy calculator, it approximately 24.57 meters per second forward. Okay, so I'm just going to extend the page there a little bit, so I'll scroll back up to the problem if we need to. But let's take those values and throw them into our handy dandy chart here. So we have our VIY is 17.21, and we have our VIX is 24.57. Okay. Now, what other values do we have? Well, let's take a look back at our problem. So we've dealt with the velocity. Let's keep going forward. It strikes the robber on the second level of a store of a mall, 5 meters above the ground. Okay, so that means we started at 20 meters high. We ended at 5 meters high. So that's a displacement of negative 15. So we'll throw that into our y value here. Now, we know one other pair of things, and that is our accelerations, because this is a projectile, which means that it always has the same accelerations of 0 and negative 9.81 meters per second squared. And now we have to take a look at what is it that we know. Okay, we look at this, and what are we trying to find? We're trying to find horizontally how far away it is. That means we are looking for our displacement in the x direction. In order to find that, we have to find a third value, because we can only solve using our handy-dandy physics equations for linear motion. A third value, we can only find another value if we have 3 known already, and we have 2 on the x side, and we can only use x values to solve for an x value. So we need to find a third x value. Now the final velocity, while it is the exact same as the initial velocity in the x direction, due to the fact that it is not changing due to our acceleration is 0, so it is the same, but it's not really a third value. It's the same value. It's the same thing. So what we need to find is our time here, because the time here, we can find that because time doesn't have a direction. It is, it's the time. So the time in the x is the same as the time in the y. So we find the time in the y here. That should give us the time in the x there. And oh look, we have 3 values in the y direction of which to use. So what we want to do is we want to be able to find that y value. Now we have a couple ways that we can go about this. Now if we try to solve for time directly, what we have to use is our second equation right here, as I'm boxing it, that delta x equals vi delta t plus 1/2 a delta t squared. And that's because it has the 3 values that we know and the 1 value that we want to know, the delta t. But if we tried doing that, we end up with a quadratic equation. Okay? So we would need to use the quadratic formula in order to solve it, which if you are comfortable with that, then by all means plug in the values and go and solve for what delta t is directly. However, if you are uncomfortable with that, and if you're okay with rounding, then what you can do is solve for the final velocity. And what we can then do with that is use a much, much less complicated formula from up here in order to solve for time, because once we know the final velocity, we can solve for time using any formula that has time in it, not just that second equation that is located in the box. So in order to solve for the final velocity, what we use is our fourth equation right here that I'm now boxing, and I'll color in a little corner of it just so that you don't lose track of which one we're talking about. So we want to solve for final velocity using that. I will copy that equation down here. And so we have final velocity squared is equal to our initial velocity squared plus 2a delta x, which when we go and we solve this for final velocity, because we don't want to solve for final velocity squared, we have to take the square root of both sides. So the final velocity is equal to the plus or minus, because remember, whenever you apply a square root in order to solve for a variable, it can be the positive or negative version of it, of vi squared plus 2a delta x inside of there. And we take our values and we plug that all in. Reminder, only use the y values because we're trying to find the y final velocity. Okay, I'll even put this over on the side here of the y just to remind us to do so. So we have the final velocity is equal to plus or minus the square root of our initial velocity in the y direction, 17.21 squared, plus 2 times our acceleration, negative 9.81, times our displacement of negative 15. Okay? When we do this, we get a final velocity of positive or negative 24.30 approximately. Now, there is only one correct answer because this is a velocity. It can't have two velocities at the same time. So, and we are talking about the same time here. So that means that it must be something that we have to take a look at and figure out. Now, if it's going up and it has a negative displacement there, really the only way of achieving that if you fired up is if you've already gone past the maximum height and you're going down at this point. So the only real correct option for us is the negative version of this, the negative 24.30, because that's really the only thing that we can use that with. And the double check for this is that if you use the positive version, you would end up with a negative time, which again does not make sense. So now that we know that our final velocity is 24.30, we can use any equation in order to solve for time. So I'm going to use our third equation of Vf equals Vi plus A delta T. So what we would then use is plug in all the values, rearrange it. We end up with an equation of delta T is equal to Vf minus Vi over A, which we plug everything into, and it gives us 4.23 seconds. Okay, so it's in the air for 4.23 seconds, and now that we know the time, because now that we know this is 4.23, I made a small mistake here, and that should have been a negative at that point, but it's 4.23 seconds on the x side as well, and now we have enough information in order to solve for displacement on the x side. The only equation that we could really use on the x side is delta x equals Vi delta t, because that's what our equation boils down to. And so all we need to do is plug in our time and our initial velocity, of which we know both. It is the 24.57 that we had before, times our 4.23, and we end up with an approximate displacement of 103.93 meters. Dang, that was a far shot. Well done, green arrow. Okay, so that is your two variable problem, and just make sure that you're always putting in the values where they need to go. Okay, don't forget that this. Oop, I almost highlighted something improperly there. These are your displacements, so they mean distance. That these are speeds, so you can only put speeds in there. Your accelerations have to go in this area, and only times can go in there. So do not confuse any of them together. You can only use three values to find another value, and they have to all be from the same side. And I will see you next time or in class. See you later.